We are Group 4 from Class F09 and this is our presentation on the effects of electromagnetic radiation for CTM. For our presentation, we'll be covering 5 main things. First, the narrative. Second, problem statement and assumptions. Third, variables and solutions. Fourth, model analysis and assessment. And finally, fifth, strength and weaknesses. The narrative. The year is 2079. CTM is at the apex of human civilization and has come a long way since its humble beginnings. The quality of life has reached an all-time high for its citizens, but now it faces a new problem, and that problem is its energy needs. With newer and newer technologies coming out, the average energy consumption per person has greatly increased over the past few years. Luckily, due to the advancement of technology, this energy demand can be met, but with a cost. CTM will have to build power plant generators that not only produce high amounts of energy, but also benefit the population with jobs and livelihoods. However, these generators emit an electromagnetic radiation similar to those of ionizing radiation. There has been much debate over the use of the generator. However, with the pressing issue of the energy crisis, an immediate solution is required. The generator has no byproducts and doesn't affect the environment in a negative way. CTM now has to decide if the cost of having these generators are worth its downsides. That is where our model comes into play. Our problem statement. Our model predicts the effect on fertility rate and economic production as a result of the increase in the number of electromagnetic generators built in CTM. These are the assumptions that we've made with our model. First would be the impact of the generators. Our group has discussed and made the assumption that the only impact of the electromagnetic generators would be the high level of ionizing radiation that affects fertility. The engineering technology and systems used in the generator have made it so that there are no negative environmental effects, which include no waste products. Next would be our assumption on the fertility rate. There is a negative relationship between the levels of electromagnetic radiation, ionizing radiation, and the fertility rate. Our research that we have done supports this sentence. The next assumption that we've made is that all generators increase the level of ionizing radiation linearly. For our last two assumptions, the first one would be the economic benefits of the generators. There is a positive linear relationship between the number of generators per unit area and the economic benefit. For our last assumption, it will be the economics and fertility rate. There is a negative linear relationship between the number of generators per unit area and the loss of fertility rate.
Our model is built on variables x and j and constants k, n, m, and y. X refers to the number of generators that will be built in CTM. J refers to the fertility rate after being affected by the electromagnetic radiation from the generators. K refers to the city's fertility rate without the effect of electromagnetic radiation. N refers to the gradient of the linear relationship between the number of generators per unit area and the loss of fertility rate. Fertility rate refers to the number of births per woman. M refers to the gradient of the linear relationship between the number of generators and the economic benefit. Economic benefit refers to the increase in gross domestic product or GDP. And lastly, Y refers to the land space of CTM in km squared. Moving on to the equation of our model, J equals K plus N times M times X over Y. Before we apply our model, we should first look at how the constants of N and M are formed. Firstly, M is formed by looking at the relationship between the amount of generators per unit area and the economic production in CTM. Economic production refers to the GDP of the country, and the amount of generators per unit area is in square kilometers. Following our assumption, there is a positive linear relationship between these two factors. Every additional generator creates jobs for the population and also increases the productivity of other sectors of the economy. Most importantly, the gradient of the trend line between these two factors is M. Moving on, N is derived by looking at the relationship between the fertility rate and economic production. As a result of the increase in the number of generators per unit area, there is an increase in the amount of ionizing electromagnetic radiation. From our research, many scientists believe that fertility rate is negatively affected by the presence of electromagnetic radiation. Thus, As the economic production and number of generators per unit area are positively related, it follows that fertility rate is negatively related with economic production. Following our assumption, there is a negative linear relationship between these two factors. The gradient of the graph is the factor n, and the vertical axis intercept is k. The fertility rate of the city without the effect of ionizing electromagnetic radiation. The gradient of this graph is the factor n, and the vertical axis intercept is k. The fertility rate of the city without the effect of ionizing electromagnetic radiation. Now we will apply the model to a few cities to see how it performs and what insights we can find out. The 4 cities that are chosen are Singapore, Tokyo, London, and Berlin. The values of k and x are shown in the table. The value of m was set to 10 million. We chose this value as it means that for every additional generator, the GDP of the city will increase by 10 million. The value of n was set at negative 0.000004. This roughly translates to a decrease in fertility rate of 0.000004 for every $1 increase in GDP as a result of the increase in number of generators per unit area. We graphed the model for the domain of 0 to 10 generators. Here are the graphs for Berlin and Singapore. This slide shows the graphs for London and Tokyo. Now to interpret the graphs. The negative correlation between the number of generators and fertility rate is logical and aligned with our research. However, there is no reference data we can use to verify the accuracy of our model. This is due to the electromagnetic generator that we based our model on not currently existing. 2 of the 4 constants, n and m, are estimations, greatly reducing the reliability of the result of our model. Contextually, we see that the gradient of the resulting graph is less steep for cities with a large land area, such as London and Tokyo. This observation aligns with the idea that as the number of generators per unit area increases, the average level of ionizing electromagnetic radiation increases, which causes a decrease in fertility.
As a result, the fertility rate decreases at a lesser rate for cities with a greater land space.
Finally, we have the strengths and weaknesses of our model. Firstly, one of our strengths is that we appropriately account for the decrease in fertility rate as a result of an increase in the number of generators. Secondly, we consider the different land sizes that City M could have to produce a more accurate result. And finally, we use fertility as the main concern that countries in the future would face. Moving on to weaknesses, the values of M and N are purely estimated. We assume that the equal distribution of generators to land size may not be a true reflection of what is a practice in the real world. And lastly, we only take fertility into account as the main hazard of electromagnetic radiation. Thank you.